In our previous work, we've been talking about minimization of sum of products using Carnot maps, but we can also do a product of sums form, and sometimes that turns out to be a little more efficient. And so if you're really looking at trying to minimize the number of terms / literals, you could also look at product of sums. Okay, so it turns out the technique for doing product of sums is really close to what we did for sum of products, only instead of circling the ones, we cover the zeros, okay? We cover the zeros and we come up with an expression for F bar, and then we apply De Morgan's theorem. Okay, so let's get started with this example to show how this works out. Okay, so the first thing we do is we have a 3-variable Carnot map, so hopefully we're getting fast at this. Come up with the 8 squares. Here's F, A, B, C. Here's A, B's over here, C's in the middle, 0, 1. All right, there's our Carnot map. We can label them in terms to make it easy to put on the map. And in this example problem, we're doing min terms 1, 2, 5, 6, and 7. Okay, so that means the other squares, we haven't talked about this, but the other squares would be zeros, right? We didn't label them, but they would be zeros. So let's go ahead and put those in red, and so that they're not a distraction, let's remove the ones. And this is our starting point for product of sums. So what we're going to do is we're going to come up with a circling or grouping that covers all the zeros, and then we're going to apply De Morgan's theorem. Okay, so looking at what we've done before, we're looking for first essential prime implicants, and this 3 stands out to me because it's just a 0 sitting there by itself. So the only way to cover that is with just a single min term. Okay. All right, then, let me change the color. Then we cover the other essential min term. The only way you would cover the 0 and the 4 is with this grouping. Okay, so since we have the zeros here, we're not really writing an expression for F. We're writing an expression for F bar. Okay, so F bar, reading the map, the blue term, spans A, it's outside of B, it's outside of C. So it'd be B bar, C bar. That is our blue grouping. Then, to read the green grouping, the grouping of 1, we look, that's outside of A, inside of B, inside of C. All right, so that's our green grouping. Awesome. Okay, so that's F bar. And what we can then do is take the complement of both sides of this Boolean identity, or this Boolean function. Okay, so if you complement F bar, you get back F, which is what we want. All right, and now we apply De Morgan's theorem. Okay, so De Morgan's theorem would say, break this upper line, all right, so it would be 2 pieces, and they would be a product. Okay, so this would be B bar, C bar, with a bar over the top, and then A bar, B, C, with a bar over the top of that. Okay, so just to make it clear, these are in parentheses, and the AND operator is in the middle. So we broke this line, and we changed this sign. Okay, so we applied De Morgan's theorem to the expression. Okay, then the next step is to apply De Morgan's again. Okay, and so when we do that, we break the line, change the sign, we'd have F bar, bar, or, the and here turns into an or, C bar, bar. Okay, so the broken line comes from this. These get broken in two, okay? And then we change the sign from an and to an or. All right, so that's De Morgan's applied to that side. And then we do it again. Okay, so break the line. We get three different parts here. A bar bar. This and turns into an or. This B has the line over the top of it. And the C has the line over the top of it. And so we can clean this up by removing the double complements. And we have B or C ANDed with A or B bar or C bar. Okay, so this is, in this case, a result that is known as product of sums. Okay, so you might ask, why would you do that? Well, if we work the same problem, so I'm going to copy this. Go down here and let's work the same problem, circling the ones. Okay, so if I'm going to circle the ones, let me put those in there in red. Oh, I forgot to delete that one anyway. Okay, and then let's get rid of the zeros so they're not a distraction. We could leave them, we just need to cover all the ones. Okay, so our point here is we're comparing the result we get when we do a K-map minimization of the original Boolean function using product of sums. I'm sorry, sum of products. Okay, so at this point, we're doing sum of products. All right, so we're looking and we need to cover, find the essential prime implicants. Okay, and so I look at, for example, 1, min-term 1 can only be covered here. So that's an essential implicant. Min-term 2 can be only covered here. And then I have a choice on how I'm going to cover 7. All right, so I'll use orange and cover that here. Let me change this because it's not the same group, different color. And while I'm on that subject, you only have one color if you're using just a pencil, and so you can do circlings to show groupings. Okay. All right, so from here, it's a matter of reading the map. All right, so we see the green term. We span A. We're inside B bar. And it's a product. B bar, and then we're inside C. We span A, so A drops out. Okay, so that's our green grouping. And then we can go to the orange grouping, and we are inside of A. We span B, so B drops out, and we're inside of C. So that's the orange grouping. And finally, the purple grouping, we span A drops out, we're inside B, we're outside of C. Okay, so there's the purple grouping. All right, so which one wins? This is an equivalent Boolean function. This is sum of products. Okay, and let me just move it here. And then I can copy my other answer. The other answer was product of sum. And we can talk about what's more minimal. All right, so in one case, we have two terms with three literals. All right, and so we've talked about, in terms of the definition the book uses, this would be the winner. Okay, but if you were going to implement this with two input gates, you would have, an extra gate that's involved with getting this three input OR. All right, so it's really a matter of the application as to what is the true minimum. But in the case that we've talked about in the book, we're defining number of terms wins over number of literals. The POS implementation is more minimal than SOP. All right, but it's really not a huge difference either way. So don't act like, we shouldn't act like we're really pursuing the absolute minimum implementation. Okay, so we do want you to know, how this process works and how to do a Carnot map. It's going to come in handy for later problems where we do more sophisticated things.